Hello, my name is Maciej Dunajski. I'm a fellow and the director of studies in mathematics at Clare College in Cambridge. I want to talk to you about how mathematicians make sense of curved spaces. This is a fascinating branch of geometry which we teach to our students at their second year. But what I want to share with you today, you should be able to follow with A-level knowledge or below. We'll start off by thinking of curves. So imagine a civilization of intelligent bugs which inhabit a one-dimensional universe, like this red curve on the left. The bugs, let's imagine, know a lot of mathematics and they can measure distance. Can they determine that their universe is actually curved rather than being straight? It turns out that they cannot. We see the curve as curved because we look at it from outside and we can take into account the way it is embedded inside the plane. But by stretching it very gently, we can turn it into a straight line without changing the notion of a distance. So if all the bugs can do is measure the distance and there is nothing else for them to measure, they just cannot tell. Turns out that the situation changes for the bugs living on the surface of a sphere. There, the curvature is intrinsic to the sphere, and if the bugs know what they are doing, they could tell their universe apart from, let's say, a plane. So I want to first explain these two concepts of extrinsic and intrinsic curvature to you. Let's start off with curves. We will approximate our curve at any given point, let's say P, by a circle of best fit. So what we'll do is we draw a tangent circle to the curve at P. Now, problem with that is that there are infinitely many tangent circles. You'll see 3 on this figure. We need to pick the best one. And the way we do it is by observing that the curve divides the plane into 2 regions. On my picture, this will be up and down. Now, some circles, like the smaller one, lie entirely in the lower region, and the big one is in the upper region. Now, if you change the radius of the circle continuously, you'll find the circle which separates the 2 families of circles. That one is called the osculating circle, and having found it, will declare the curvature of the curve to be a reciprocal of its radius. Well, for example, if the curve we want to measure a curvature of is a straight line, then the radius of the osculating circle, or in fact any other tangent circle, would be infinite. We can think of a straight line as a limiting case of a circle with infinite radius. So the curvature of a straight line is 0. If the curve is itself a circle of, say, radius 1, then its curvature is equal to 1, and it's the same at any of its points. Now, you would want to be able to measure, in fact, compute the curve for a general graph of a function. So think of a red curve as a graph of a function y equals f of x. To do that, you have to employ calculus and first realize that what's special about the osculating circle is that it shares not only the second, but not only the first, but also the second derivative at the point P with our curve. Now, if you do that and do some algebra, and I think this is within your reach, this is something you can try, you'll find that the curvature of such a curve is given by the ratio of a second derivative of f and the expression involving a square of the first derivative. So that much for curves on the plane. Let's move on to surfaces, and I'm going to define a curvature of a surface by slicing it into curves. And this concept and what follows goes back to Carl Friedrich Gauss, who was a German mathematician, broadly regarded as the greatest mathematicians of all time. And yet what I'm going to tell you about, one of his great theorems, he was the most proud of. Well, what Gauss says we should do is the following. Given a surface, choose a point. Let's say this point is where the two curves cross, and slice our surface with planes which are perpendicular to it at this point. And there'll be infinitely many of such planes because you can just rotate a given plane, keeping it perpendicular. Now, the intersection of any of these planes and the surface is a curve. So we can compute its curvature, and we can also decide that if the curve bends downwards from the tangent at the point, then its curvature is positive, and otherwise it's negative. So for this surface on the diagram, this curve would have a positive curvature, and this one would have negative curvature. Well, we'll now pick the maximal possible curvature of a curve we get, call it kappa max, and the minimal one, which can be negative, call it kappa min, and declare its product, call it capital K, to be the Gaussian curvature of our surface at the point. And for a general surface, this curvature will vary between points. The surface can be more curved at some points, less curved than others. So let's look at some examples. For a sphere, you see, whatever point we choose, the only curves we'll get by slicing it with perpendicular planes will be circles. And the circles will all bend in the same direction. So if the radius of the sphere is 1, then kappa max and kappa min will both be equal to 1, and so will the Gaussian curvature of the surface. Well, the surface of a sphere has a positive Gaussian curvature equal to 1. The next example is a cylinder. You see, there we have various possibilities. We can slice a cylinder in a circular curve. This would be choosing a plane which is parallel to the base of the cylinder. If the base circle has radius 1, then this curve would also have radius 1, so its curvature would be 1. But we could also slice the cylinder with a plane which is parallel to the axis, and that's a straight line. And the straight line has 0 curvature, so in case of a cylinder, kappa max equals 1, kappa min equals 0, and the total curvature at any point is 0. We'll say that cylinder is flat, and in fact it is. If you take a pair of scissors, you can cut it along one of its generators and flatten it to a plane. You cannot do it with a sphere. The last example, I'm sorry about that, will be a surface of negative curvature, like this saddle of a horse. Here, some curves bend inside the saddle, like the light green one, and others bend outside. For the example I've chosen, they are both circles of the same radius, but because of going inside and outside, you'll take one radius with sign plus and one with sign minus. So the total curvature of the saddle point surface is -1. Now, let's go back to our bags. Can they use what I told you about to measure the curvature? Well, they can't really, because I've used extrinsic concepts of planes intersecting the surface. And to do that, you must view the surface as being embedded in 3 dimensions. But there is another equivalent way to determine the curvature, and this is what Gauss has discovered. And to tell you how to do that, I'll need to define geodesics. So a geodesic on the surface, the geodesic between 2 points is the shortest path, if one exists, connecting these 2 points. For example, on the surface of a sphere, a geodesic is a part of a great circle. This is like an equatorial circle, which you'll obtain by intersecting a sphere with a plane which goes through the center of the sphere. And this is the shortest. You cannot do any better going from P to Q. Well, you might be tempted to go from P to Q along a line inside the sphere, but that'll be cheating because you'll be moving away from the surface, right? You can only choose curves on the surface. Now, once you defined a geodesic, you can talk about triangles. So let's think of a surface of a sphere, pick 3 points, call them A, B, and C, and connect A and B with a geodesic, and B and C with another one, and also A and C. So we have 3 segments, three lines on the sphere. They form a triangle. You can then add the angles of these triangles, and to do that, to measure the angles and to measure the geodesics, you do not have to move outside the surface of a sphere. You'll then find that on the sphere, which is positively curved, the sum of the triangles is always greater than 180 degrees. On the plane, you know, the sum of the angles in the triangle is equal to 180. And on the surface of negative curvature, like the saddle point surface, saddle type surface, the sum of the angles is smaller than 180. So this is one way in which creatures living on the 2-dimensional universe, a surface, can detect its curvature by constructing the triangles and measuring some of the angles. There is another way which actually leads to a formula. You see, pick a point on the surface, and this bit will not assume that the curvature of the surface is the same at every point. You could do that at any chosen point. So you pick a point and you look for all other points which have the same distance on the surface from your chosen point. These points form a circle on the surface. Now, you know that if this was a circle on the Euclidean plane, then its circumference would be 2 pi times the radius. It turns out that this formula needs a modification in the presence of curvature. On positively curved surfaces, the circumference is smaller, and on negatively curved surfaces is larger. And in general, for small circles, the correction to the 2 pi r is given by minus the Gaussian curvature times pi times r cubed over 3. The dots here denote some higher order terms which involve higher powers of the radius, but if the radius is small, you can neglect them and read off the curvature just from these. And now, other practical problems where curvature comes into play, and when you would want to know whether a surface is curved or flat. Well, the earliest of such problems, I think, go back to cartography, to map making. You would, once you realize that the surface of our planet is spherical, you ask whether you can map it onto a plane in a way that preserves distance. And this, it turns out, is impossible precisely because of the curvature of the surface. There are several ways of making maps, but they all distort distances in one way or other. I'll tell you about 2. The first one is something mathematicians really like to do. It's kind of interesting mathematical procedure, but not a very good cartographical device. We call it a stereographic projection. To do that, pick a point on the surface of the sphere. Let's call it the North Pole. And in coordinates, let's say 0, 0, 1, if the equation of the sphere is x squared plus y squared plus z squared. Now, for any other point, P on the sphere, connect the North Pole and P by a straight line in R3 and see where this straight line hits the XY plane. And so this gives you some point P prime, and this is the image of a point P under this stereographic projection. And you can do it with any other point on the sphere, except the North Pole itself. So in that sense, a sphere is the same as a plane, because every point on the sphere has an image on the plane, together with an extra point. We call it a point at infinity, which corresponds to the North Pole. Now, if you use the idea of similar triangles, then you'll find that the complex coordinate of the image of a point with coordinates x, y, z on the sphere is given by this expression. And you'll never have to worry about dividing by 0 because you've excluded the North Pole from your projection. So z is never equal to 1. Now, this procedure wouldn't be any good if you wanted to make a map which fairly accurately represents distances. And that's because the regions close to the North Pole are mapped into huge regions of infinite area on the plane. On the other hand, regions close to the South Pole are mapped into regions with tiny area. So there are better ways, other ways of making maps. And one of them, and the one we still use today, goes back to a projection devised by Mercator, who has constructed, using a fairly advanced for his days mathematics, has constructed a map with a property that every straight line on his map is a line of constant compass bearing, they called rump lines. Now, so if you had a chance ever to cross the Atlantic on the plane, and maybe you did it before the days of on-flight entertainment, you would have noticed that on the in-flight map, the trajectory of a plane is not a straight line, but it's curved like this segment here. And this is not because, as people would want to tell you, your plane tries to navigate towards Greenland to be able to refuel, but because this red curved line is in fact a geodesic on the sphere, but it appears curved on Mercator's map. You cannot, because of the curvature, construct a perfect map. Now let's take a step back, in fact, a big step back, go back to the 4th century BC, where Euclid of Alexandria wrote what is regarded as the most influential mathematics book ever written, the Elements. In this book, he laid down well, first of all, he really introduced what we think of the axiomatic techniques in mathematics. First you define things and then you try to prove theorems about them. He wanted to axiomatize geometry and prove some statements about geometry of his axioms. And he formulated 5 of them, also called postulates. They 4 are intuitively obvious. First one, exactly one straight line segment might be drawn between any 2 points. Well, that's true. You'll see that when you experiment with lines on the plane. A piece of straight line might be extended indefinitely onto an infinite line. A circle might be drawn with any given radius and arbitrary center. Indeed, there'll only be one such circle. All right angles are equal. That's a bit odd. What that one means is if you take 2 right angles and you keep one where it is and the other one you translate and possibly rotate, then these 2 right angles will coincide. So up to this congruence on the plane, all right angles are the same. And then the 5th axiom, known as the parallel postulate, states this. Given a line L and the point P not on the line L, there is exactly one line which contains P and doesn't intersect L. So on this diagram, you have L and you have P, and the light gray line is the unique line of Euclid's axiom. Now, this 5th axiom caused controversies which lasted for over 2,000 years. You see, if you have a set of axioms, you'd like to know if they're really independent. So can it be that the 5th axiom, in fact, can be deduced from the first 4 and didn't have to be put by hand in the first place? It turns out that Euclid was right because there is an example of a geometry, we now call such geometries non-Euclidean, where only the first four axioms hold, but not the fifth one. So this is what I want to tell you about next. This is called the hyperbolic geometry. And the model I'd like to use is known as the Poincaré disk. In fact, it was discovered by Beltrami, but not unusually in mathematics named after somebody else. So this disk is just an interior of a circle with unit radius. You can think of it, if you know complex numbers, as complex numbers of modulus smaller than 1. Now, what are the geodesics on this disk? Well, so what are the shortest lines? Well, they're of two types. If 2 points you want to connect line on the diameter, then the geodesic connecting these points will be part of the diameter. And otherwise, the geodesics are circles which intersect the boundary of our disk at 90 degrees. It turns out that you can connect any 2 points on the disk uniquely, either by a diameter or by such a circle. Now, having defined these geodesics, you then ask, is there a notion of a distance which these geodesics minimize? And there is. And the way you compute it is as follows. Let's pick 2 points, P and Q, and connect them by a geodesic. This geodesic will intersect the boundary circle at 2 other points, call them A and B. Now, the distance between P and Q is obtained by computing Euclidean segments, the length of Euclidean segments AQ, AP, BQ, BP, and forming this expression AP, BQ divided by AQ, BP, and taking its natural logarithm. And that assigns a number to a pair of points, and this, it turns out, and for that you really would want to study geometry at the second year in Cambridge or somewhere else. It turns out that this geodesics minimize this distance. In fact, this is a curious notion of a distance because the points on the boundary of a disk, if you were to compute the distance between such a point and the origin of the disk, you would find that it's infinite. So the boundary is infinitely far away from the origin. And this explains the paradox of this tessellation of a disk, which I took from one of the pictures of M.C. Escher, a famous Dutch artist who visualized many concepts in hyperbolic geometry. There are angels and devils on these pictures, and from our Euclidean perspective, the devils towards the center appear larger than those near the boundary, but they in fact all have the same size, but you have to take the hyperbolic distance into account. So this, you can check that all the 4 axioms of Euclid, the first 4 axioms are satisfied for this model, but the parallel axiom is not. Because, let's say we take point Q, you'll see that there are 2 lines, this one and that one, 2 geodesics on the disk, which go through Q, and they don't intersect this geodesic, which doesn't go through Q. In fact, there are infinitely many parallel lines, lines which are parallel to the diameter, which go through Q, but don't intersect the diameter. So that's a non-Euclidean geometry for you. The parallel postulate fails, and the Gaussian curvature, if you wanted to look at the triangles on this disk model, you would find that its angles add up to something less than 180 degrees. And in fact, its Gaussian curvature is negative and everywhere equal to -1. Now, to finish off, I'll move away from surfaces and I'll talk about curvature for concepts in higher dimensions. I'd like to talk to you about the curvature of the universe. You see, I'll step up in dimensions, but I step down in precision and rigor. We think of curve as one-dimensional. It has 1 degree of freedom. a surface has 2 degrees of freedom, for example, a longitude and latitude in the sphere. From what we learn in Einstein's theory of gravitation, we should think of our universe as 4-dimensional space. We call them manifolds. And this one will be called space-time, consists of 3 space and 1 time dimensions. And it's also curved. Now, the message from Einstein's theory is that the gravitation we perceive is in fact an effect of the curvature of space-time. So here you have a picture of a planet circling a very heavy star, and it looks like this planet is moving along a curved trajectory. In fact, it's moving along the shortest possible path, but on the curved space where the curvature is caused by the star. Now, Einstein's equations make this precise. I'm writing them symbolically here. They tell you how mass of the universe or region of the universe is translated into curvature. We now know, both from observations and analysis of Einstein's equations, that there exist regions in the universe where the curvature is infinite. There are 2 types of such regions. The first one is the Big Bang, which we think of as the beginning of our universe, beginning of space and beginning of time. And then there are black holes. The black holes arise from collapsing of very heavy stars, where the density of these stars becomes so large that the gravitational attraction pulls things together to infinite density. So inside black holes, physics as we know it breaks down. Mathematics just about tolerates infinities. Physics does not. We don't know what to do. And that, I think, is a good place to stop. Thank you.